eigenvalues in non-commutative division algebra. Since product in algebra is non-commutative, I consider two forms of product of matrices and two forms of eigenvalues. Then I consider solving of homogeneous system of differential equations. Let A be associative division algebra or commutative ring D. We also say that this is associative D algebra. Also, we consider left or right model V over division D algebra, and usually this model is called vector space. According to the custom, the product of matrices A and B is defined as product of rows of the matrix A and columns of the matrix B. But in non-commutative algebra, this may create some problems. Let's consider two examples. Let E be basis of right vector space. We represent the basis E as row of matrix. And we represent coordinate of vector V as vector column. Therefore, we can represent the vector V as product of matrices E over V. However, in left vector space, if we represent vector E as row basis and vector V as column, we can't represent the vector V as product of matrices. Here, also I want to know that I assume the Einstein summation rule, where if index is repeated, we assume the sum over this index. So, these two examples show that we cannot confine ourselves to traditional product of matrices, and we need to define two type of product of matrices. So the first type, let number of columns of the matrix A equal number of rows of the matrix B. Then we introduce a row column product of matrices, where we see here a row of matrix A multiplied by column of matrix B. Similarly, let the number of rows of the matrix A equal the number of columns of the matrix B. We introduce column row product of matrices, where we see that in this case we multiply column of matrix A over row of matrix B. In non-commutative case, it doesn't matter for us, because if we change the order of the matrices, then row column product change to column row, right? Vice versa. We use these symbols to distinguish these two types of product. No, it's easy to remember because I usually write symbol star on the place of the index of the cofactor. And we read this symbol as RC product or row or column. And this symbol we read as CR product or product of column over row. Also, I introduce matrix delta as identity for both products. For each type of product, I can introduce power. For instance, RC power of matrix is defined as 0 power is matrix delta, and n power I introduce as product of n minus 1 power times A. No, also inverse row column inverse matrix is defined by equality to 8. And similarly, I introduce column row inverse matrix, which introduced by equality 2.9. In non-commutative algebra, we cannot introduce definition of the determinant because it's not clear in which order we should multiply entries of the matrix. On the end of the last century, Professor Gelfand and Professor Retov introduced definition of quasi-determinant, which they calculate by equality 3.1, is formal equality. In general, property of quasi-determinant is very convenient in the theory because they allow to study linear algebra the same way as we do in commutative algebra. But calculating of quasi-determinant itself is a very complicated issue, and if I need to calculate quasi-determinant of order 3 or higher, I need to use computer software. However, for quasi-determinant of order 2, expressions are relatively simple. For instance, row column quasi-determinant, we can use mat 3.3, and column row quasi-determinant, we can use equation 3.4. Also, I need to put attention that matrix may be row column singular and column row regular. So it's to be singular depends on the order I which use matrix in the product. Now, inverse matrix, you see, if you compare these two expressions, you see that this is transposition of the matrix, and I get from each element its inverse. So this inverse matrix. We will use this later in some calculations. Because I have two different types of products, I have appropriately two different types of eigenvalues. So I use row column eigenvalue if matrix of this type A minus BE is row column singular matrix. And for RC eigenvalue, I can use or eigen column vector, which is defined by this equality, because on the right side I use column vector. If I get product from the left side, this will be row vector, so it will be eigen row. I just make a distinguish in the definition to make sure what type of vector, how I present the coordinate of the vector. And similarly, I can introduce column row eigenvalue, and for column row eigenvalue, I see appropriately eigen column vector and eigen row vector. But in this case, vector is written from other side. Before I start to learn differential equation in non-quantitative algebra, there is one more definition which is important for me. For any B in element B in algebra A, there exists an algebra which I call center of number B, and element of this algebra commute with this B. Now it's evident if C commutes with D, the D will commute with C also. So this such type of statement 5.2. Long time I tried to introduce exponenta using differential equation, but in quantitative algebra it's not easy equation. So I confine myself to standard definition as row series. And easy to show that if x get by this equal map from a real number, and because any real number commute with element of algebra, then I just can use such type of series, a n to m and from 0 to infinity. Here is also important because I can use the series, I can use by induction over n, that if C conveys with A, then I can write in the product C or on either side or exponent times C or C times exponent. In particular, for any A, this holds this equation: exponent times A equal A times exponent. In non-commutative algebra, in general, derivative is tensor product. But when I have map from real number to algebra A, then any order of derivative will belong to algebra A. In particular, we can prove equation that is known from incommutative algebra. Then any order of exponent is exponent times a in power n. And a in power n I can write on either side, on left, on right. Now, if I have a differential equation, this over the t equal ax, a is written, constant is written on the left side, then solution I can write like exponent in power at, but constant c is written on the right side, on the opposite side from a coefficient. No, first of all, we can test that this expression is really solution of our differential equation. So you see that I selected by red color trial function. You see that it satisfies the equation. To answer the question whether we can write a constant to the left of the exponent, we consider the following lemma. Let A be Banach the algebra, and for any numbers C1 and C2, the map C1 times exponent times C2 is the solution of differential equation only if and only if C1 conveys with A. No, it's easy to see that if I put this map to differential equation, that C1, C2 can go outside of derivative. A I can write on either side, but here's very important moment. Because if C1 doesn't commute with A, I cannot change their order. And therefore, the trial function is not solution of differential equation. But if C1 commutes with A, I can switch the order C1 and exponent. And therefore, the solution will be exponent times C1 times C2. So it doesn't matter. I multiply C1 and C2, and ultimately I will get the initial form of the solution. So constant should be written on opposite side from coefficient in differential equation. So a similar theorem is not necessary to prove it because it's just mirror expressions. If coefficient is written on the left side, then arbitrary constant is written on the right side. Now I consider a system, a homogeneous system of differential equation. Because we have a product on the left side, on the right side, it is a reason to write a coefficient of the same times altogether. So here, coefficient is written on the left side, and a known function is written on the right side. If I represent a set of function as column vector, then the derivative will be also column vector. A set of coefficients will be matrix. And I can write this equation as RC product. So dx or dt equal A RC product X. And using the theorem for one differential equation, I will introduce solution in the form x равно e in power bt times c, where c is a column vector of arbitrary constant. Now I will consider two theorems which put some limits on the value of b and type of matrix C. Let B be RC eigenvalue of the matrix A, of the matrix of differential equation of this matrix. And let B convolute with each entry of the matrix A. This condition implies that matrix of map 6.3 is solution of the system of differential equation for RC value for RC column C. First of all, we try our equation. So we see that if we substitute not our equation here, we get after differentiation on the left side, a in power bt bc. On the right side, we have RC product A is a b exponent times c. Since exponent, since b commute with each entry of our matrix, we can change their order. So here in power bt, we can put on the left side of our matrix. Because in general, exponent is different from 0, I can just write the equation bc equal a RC product on C. But this is a definition of eigenvalue B, and also tells us that C is RC eigen column. So this works. Assume that B does not commute with each entry of the matrix A. In this case, I can write column C as product of column C1 times P, where P is any A number. Then I request that C1 commutes with B. Each entry of the matrix C1 commutes with B. This is also a choice when my expression will be solution of the system of differential equation. Now again, we can try it. And we see on the left side that we have b times exponent. C we represent in this form. And on the right side also we have, because p is constant, is any and a number, we can put it outside of the product of a matrix. And for us, p is now not important. We see that expression b, if exponents, because C1 commutes with B, we can change order C1 and B. So exponent here appears on the right side. And again, because exponent in general is different from 0, we can reduce for this exponent, and we have equation A C product C1 equal B times C1. And again, I see that B is eigenvalue and C1 is eigenvector. If B doesn't hold any of these requirements, that appropriate eigenvalue B is not good to be chosen for our solution. Some mathematicians consider trying to write constant not on the left side, but on the right side. What happens in this case? In this case, we get equation like 612, and if we return to the choice that we considered on singular equation, you see that requirement this solution to be uh, solution of our system should be that B commute with C. But if B commute with C, then we can change here order and get solution. For this reason, this type of solution, they call it left and right eigenvalue. I don't consider because left eigenvalue is not good to choose our solution. No, and also it's easy using math induction to see that any derivative of order n of matrix is written like n power of matrix A times x. And if we summarize all this all together, you can get a solution of our equation in the form exponent of the matrix times vector C. The same as we have in commutative algebra. And this make good choice of a relation between Lie group and Lie algebras. Similarly, if I have a constant written on the right side, then in this case I have column row product, and instead of RC eigenvalue, I get CR eigenvalue. But in general, theorem looks similar way. We constant right on the left side now, and we require that or B should compute if A is the entry of the matrix A, or arbitrary constant that we choose for our solution should compute with eigenvalue B. And again, we can to make if we add any arbitrary P on the left side, then we get also solution. So it's easy to see that in either case, do we use left or right system of differential equation, the set of solution creates left or right vector space or algebra A. Now I consider very simple differential equation. It's dx1 over delta x equal x2, and dx2 over delta x minus x1. Here is matrix is very simple. And because it's real number, it's very easy to see that any solution that I will find will satisfy the set of differential equation. And because I have deal with real numbers here, then quasi-determinant will coincide with determinant. And I have equation b squared plus 1 equals 0. Here we see very unusual situation because in quaternion algebra, this equation has infinitely many solutions. Mainly, any solution of this equation has form b1i plus b2j plus b3k, where norm of this vector is equal 1. So it's like circle around 0. If I consider this RC system, then I should write equal solution of this equation in the form a in power bt, where b has this form, times 2 vector c1, c2. And if I put this into requirement that C1, C2 should be eigenvector, then I get between them equation minus B C1 plus C2 equals 0. So the general solution of the system has form x1 равно equal exponent, x2 equal exponent times b. So at first time is you get impression that if I want to choose such type of initial value, that I have too many choices because I have infinitely many fundamental solutions. But in particular, if I get towards B1 and B2, then ultimately I get a solution like C2 equal minus C1, and C1, no, B1 minus by 2 times C1 equal 1. And for instance, let B1 equal I, B2 equal J, and when I solve these equations, I get solution in the form x1 equal difference of two exponents times J minus I over 2, and similar expression for x2. A long time, I was absolutely sure that this solution is different from regular solution sinus of cosinus. But recently, and I will show theorem below, it proves that this just simple little different form of writing sinus and cosinus. So this is not new solution. Theorem. We can represent the solution of this system. Yeah, just repeat, not to refer to long-standing system. Just try to write it once time more. But I can choose the solution in the form sinus t times for constant, sinus t plus cosinus t, and here for constant, for quaternions, where this quaternions is any quaternions. How I get this solution? It's very simple. I just using basis 1ijk, I present expansion of function x1, x2 over quaternions. And at the same time, I will represent expansion of derivatives. So for any quaternion, component quaternion 0, 1, 2, 3, I have 4 independent system of differential equations. Each system of this differential equation have very standard solution. x1 equals sinus t times c1 and cosinus t times c2, and similar for x2. And index I have 0, 1, 2, 3. So back, if I put back my basis, then I get ultimately this solution. This is what I got this Saturday, and this helped me to find proper answer to the question. To better understand how to work with solution, I introduced Wronskian matrix. No, it's some combination of fundamental matrix and Wronskian determinant. So the idea is if I have solutions x1, xm, I just put this column in the matrix and need to decide, are they linearly dependent or independent? So getting back to my system of differential equation, I considered solutions. First solution, exponent in power it, exponent in power jt, and exponent in power kt. And the solution that I got above in example. Now it's easy to see from Wronskian matrix that this column right linearly dependent from columns xi and xj. The next step, I want to draw columns xi, xj, xk, which first impression that they really should be linearly independent because the value of columns depends on value of t. To make sure to answer the question if they are linearly dependent, I wrote a system of linear equation 9,2 and 9,3. And appropriately, matrix of this linear system is matrix A. Now, first row exponent and second row I multiply by I and j. And quasi-determinant of the system has form like written here. To get inverse matrix, I get transpose and inverse values. So because here IT, this will be minus IT appropriately. So the solution of this system, I get RC product and get that x1 is exponent, this constant, and again exponent. And x2 again exponent and conjugated constant, again exponent. But even these values are dependent on the t. If I put into this expression that exponent has expressed for cosinus and sinus, I get ultimately that x1 is just quaternion, it doesn't depend on t, and x2 does not depend on t. But it means that in this expression, ti and tj doesn't depend on t. So the column of the matrix xk, xi, xj are linearly dependent. Even more, this gives me very interesting equality that exponent in power kt, exponent in power it plus this constant equal exponent in power jt plus multiplied by this constant. So it's a little bit very unusual because in commutative algebra we know that exponent mainly works like transformation of sum into product. Here works opposite because I have and even more when I go to non-commutative exponent, not each time exponent of a times exponent of b equal exponent of a plus b. I should require that a b should commute. Here I have little different because I still have sum exponent, and here on показатель экспонента I have their product. Probably it has some relation to algebra Lie, but I need to learn it a little bit more. It's a very interesting issue. And also it's very easy to see if I'm the same expression exponent it has through exponent of kt, exponent of jt. So this solution works circle round. I can change all exponent and equality will hold. Okay. Now I'm ready to consider differential equation, homogeneous differential equation of with constant. Originally, I tried to put constant on the both sides of derivative. It's very complicated issue. Maybe I will consider this later. But when constant is written on the left on the right side, no, this case, the constant is written on the left side from exponent. Then I can introduce variable like in commutative case, x1 and xn. So I get such type of system differential equation. Now again, I write this in matrix form, and assuming the theorem that I considered above, I see that B should commute with each entry of the matrix. So this means that B should commute with each value A1, A2, An. In this case, I have a solution in the form of sum of exponent. Or I can do a little different thing. Because I know that exponent, no, there was theorem above that n derivative exponent will be bn times exponent, etc. And ultimately to this exponent. And if c is any value that I can get rid of the c, that I have request that b should be root of this equation, just like in commutative case. But in this equation, I see that b should be written on the left side from coefficient. Similarly, if I coefficient write on the left side, again, doing the same things, I get a similar equation, but in this case, we see it, I should write constant on the left side from the matrix. And again, I have requirement that B should compute with each entry AI. And in this case, I get algebraic equation for matrix for value B. No, situation very similar to which I have on commutative case. And last question that I want to introduce here is eigenvalue of multiplicity 2. I consider just a simple case when I have single eigenvalue j. And in this case, I can write a system of differential equation in this form. And I see that in this case, I again have a very standard solution in the form x1 exponent times any constant, or t times exponent and times t any constant. For me, it doesn't matter where I should write t, because t commutes, t is a real value, and it's commute with any quaternion. I didn't consider because time was very short, but I want to consider what happens if I have multiple, infinitely many eigenvalues. I need to see how will look algebraic equation for them, and how I can understand that any of these values will have multiplicity more than one. Okay. One more question that is very important here. We write a system of differential equation relative selected basis. In our case, when we use quaternion algebra, we use usually basis 0, 1, 2, 3. If I put basis here, then ultimately I get that system has invariant form. Dx for the t equal e. No, this is invariant form. but I may change basis. And if I change basis, the coefficient of system also change. Assume I have another basis, E1, and B is a transformation that maps one basis into another basis. In this case, vector X has transformation, like we have in 12.5, transformation of vector X. And if I put it all together into my differential equation, I get that in relative new basis, system of differential equation will have little different form. Dx1 over dt equal A1 times x1. So matrix A1 has some transformation to matrix, and ultimately transformation has a very familiar form. B times A1 times B in power minus 1. No, I need to fix there because it should be RC product. But what is important? In commutative case, it doesn't any change for eigenvalues, because if I get, I need to get determinant of matrix A minus lambda E. And this determinant does not change when I use matrix B and B in power minus 1. But in non-commutative case, it may make some changes in the basis. And the question is how it will reflect the solution itself. So I need to understand how much solution depends on the choice of the basis. Ну, this main subject. If you want, я не знаю, может быть, тогда мне показать немножко из... Я могу тогда насчет экспонента показать. Сейчас, давайте. Буквально 5 минут. Very interesting issue about exponent. Yes. Is very interesting issue because when I get derivative of exponent, then I have a set of functions that are not first. This is first of all that exponent does not commute, and значит, when I get derivative exponent of any order, I get expansion, Taylor expansion that is different from exponent. And this set of functions I call quasi-exponent. Their behavior is very similar to exponent. But unfortunately, when I go to real variable, function of real variable, this function disappears. Okay, let's let us finish on this because we prepared this. So I'll finish.
Well,
наверное, может, если есть вопросы, потому что, в принципе, я основной текст рассказал.
Let us thank the speaker, first of all. And if anyone has questions, welcome.
May I ask you, Misha?
Ask me?
Well, no, I mean,
Yeah, of course you may ask. Sure.
What is the principal specificity of quaternionic skew field? I mean, what is wrong if you take, for example, octonions?
The problem with octonions that their product is not associative, and for this reason, this will be, in general, there will be no big difference. But to make sure that I can work with octonions, I need to make sure that I can solve some linear equation in octonion algebra. I yet not tried. At this time, I work with texts which were supposed to solve some linear equation in octonion algebra. But I interrupted because I see some interesting issue for differential equations, so just interrupted for short time. But here one more issue. In quaternion algebra, I can use directly quasi-determinant to solve linear equation because quasi-determinant heavily relies on associativity of the product. I cannot use directly quasi-determinant to solve linear equations on octonion algebra. But what I recently discovered that set of linear maps of any algebra, or quaternion or octonion, is also vector space over this algebra. And I want to try to use this idea to solve linear equation of octonion algebra. I think it should not be a big difference, but I think there will be some very interesting issue. I know when because I step to new field, sometimes appear some unexpected issues. Also, what make difference of quaternion from commutative algebra? The fact that I have product from left and from right. And for this reason, derivative in quaternion algebra is not quaternion function, like we have it in commutative algebra, but tensor product. So I multiply left and right side. Like derivative of x squared is x dx plus dx x. It's, I cannot switch to a regular product to single quaternion. System of linear equation that I consider here more simple because this function of real value, and for this reason, this derivative is just like multiplication for a regular quaternion. This is what makes this little easy. But even so, I need to use quasi-determinant to solve differential equations.
And did you try to avoid the quasi-determinant, say, to using, say, GDEq or gating?
Yes, it's possible in quaternion algebra to use GDEq or double determinant, like it use Professor Kirchey from Lvov. But my goal to use not quaternion or octonion algebra, just to make sure that I can work in any algebra. For instance, I can consider this way differential equation relative matrices. But this algebra doesn't have such property like conjugation like quaternion algebra. So you cannot use here double or the determinant. So I need use anyway. I need to use quasi-determinant. The problem of quasi-determinant only complexity. But it's good theoretical tool. It allows to study me to some properties in general. If I need to use some practical, I think I should write some computer software like using F# or Prolog, something like this.
Mm-hmm. Yes, it's very practice to use quasi-determinants in non-abelian cases, not only for linear equations, but also for non-linear, for such like, for example, like for Toda chain, and using relations between quasi-determinant of special form, say Hankel or templates like quasi-determinants. You can write very nice relations between say, but I think nobody did it for quaternions. For example, just precisely studied generalization of such interesting equations like Penlevet-2 equation.
Yeah, I understand. Quaternion is relatively simple algebra, but again, my goal ultimate use. Maybe I will go next step. I want to see what to have octanions, and then maybe I can.
Why not Clifford algebra? I mean, some just for Clifford
yeah,
algebra.
probably, or Clifford algebra, or infinite dimensional algebra. Why not to try and to see how it works?
Mm-hmm.
But
Okay.
infinite dimensional algebra, I think I have problem with quasi-determinant also.
Of course, yes, but
probably there will be some different tool also. I will see. I need to see how it works, because
yeah, there is an interesting and open problem about how to handle quasi-determinants and all this stuff if you have zero divisors. That is really it is very challenging.
I'm looking for problems that need immediately for physics or some application to make sure that it can work, but I'm still on the way to find some good application.
Okay. Thank you
Very much.
and thank you for your talk.
Yes.
May I make one remark? Oh, sorry. Yes.
Yes. May
I make one remark? You release me. I'm sorry. It is not question. Maybe it is as a remark. Suppose somebody asks question. Is it possible to use these formulas for Z2 for super algebra for in the case if we have super mathematics, because it is not commutative. I just want to tell you just one remark, that in the case of super mathematics, we don't need quasi-determinants. I don't know. Because the situation will be much simpler that quasi-determinants. Of course, in the case of quaternions and the question that when Volodya asked question about Clifford algebras, it's really very important to use quasi-determinants. I just want to tell you that in the case of super mathematics, in spite of the fact that we have to use Berezinians, but formally becomes much more simple. I'm sorry, it's
possible. It's possible, but.
Okay, so I'm sorry, maybe.
No problem. I think it's some like possibility. Thank you.
Okay.
All right. Any more questions, comments? Well, if we have no questions, let us thank the speaker again.
Thank you very much.
And I think that's all.